We hear you?
Yes, can you hear me?
Yes, we can.
Okay,
Okay, the
brilliant.
floor
And
is yours.
you can see my slides?
Yes.
Awesome. Okay, so first of all, I would like to thank the organizers for setting up this inspiring meeting and for giving me the chance to speak here. And I want to talk a bit about quantum jumps and microscopic heat engines. And this is a project that goes back to my time at Aalto University, and the research was mainly done in the group of Christian Flint and together with Paul Menzel, who is a PhD student of his. Here's the outline for the next couple of minutes. I want to explain the motivation for this project a little bit from some recent experimental developments. Then I want to show a theoretical model for a Qubit engine and explain our results. And in the end, I would like to put this all in a bit more general context. Okay, here we go. Let's briefly talk about calorimetry. What you see here on the left is probably one of the first calorimeters that was used by Laplace and Lavoisier in the 18th century. And it works in a very simple manner. Yeah? You have an inner chamber where you put your experiment. For example, Lavoisier famously put a guinea pig into this apparatus. And then the outer chamber is filled with ice. You run the experiment for a certain time, and in the end, you measure how much ice has been melted to water. And this figure gives you an indication for how much heat was produced by your system during the experiment. What you see on the right-hand side is a bit more recent picture. It's a snapshot taken from a recent paper from the group of Jukka Pekkola. And the device that you see can be considered, I think, as a close precursor of what could be justifiably called a quantum calorimeter. And the idea is pretty much the same. So you have, again, a reservoir, which is now reduced to a small metallic island, and you have some system. Let's assume it's just a two-level system. And whenever a transition happens in this two-level system, it emits a photon. This photon is then channeled into the island and absorbed by the electron gas in the island. And because at low temperatures, the electron gas is firmly decoupled or nearly decoupled from the bulk of the island. You have an intermediate relaxation process, so the electron gas settles to an equilibrium state whose temperature is slightly elevated compared to the bulk temperature of the island. A crucial instrument you need now is an ultra-sensitive electron thermometer, and that's what the experimentalists have been working on for long now. And if you have this with sufficient accuracy, you can detect these small spikes in the temperature of the electron gas before it settles to the bulk temperature of the island again. Okay, now obviously that would be a brilliant device to study all sorts of thermodynamic processes in the quantum regime. And today I want to talk a little bit about how we can use this to understand quantum engine cycles. And for the next part of this talk, I will always assume that our system here is a superconducting qubit, which is described by this Hamiltonian here. You have two parameters. Delta is the tunneling energy, that's a device constant. V is some energy bias, which can be externally controlled with a magnetic field. And we assume that we apply some periodic modulation, which gives us the possibility to extract work from the system. At the same time, we have to provide some input to the engine. To this end, we assume that the base temperature of the island is periodically modulated on a time scale that is much slower than the relaxation time of this whole island, and certainly much slower than the relaxation time of the electron gas. So everything is well separated. And in this case, this modulation does not impair the functioning of the thermometer. And you can extract these kind of temperature traces from the hypothetical measurement. Yeah, so what you see is the temperature, the instantaneous temperature of the electron gas minus the base temperature. So these are really just the fluctuations that are caused by the emissions and absorptions of single photons. And from this temperature trace, you can now extract something that's called a quantum jump record, which is presumably the closest thing you can get to a classical stochastic trajectory in a quantum setting. You have stochastic jump types tk, and the variable dk indicates whether a photon was absorbed or emitted. Now, before moving on, I would like to note that there has been a lot of theoretical and experimental work on this setting over the last almost 10 years now. I'm just mentioning 3 papers here, but this list is by no means complete. And for a complete list of references, I would refer you to our paper, let's say a more complete list of references. Okay, let's move on. Now, what can we say about the system from these temperature measurements? We can now extract the power of the engine cycle, which is just the total produced work divided by the cycle time curly T. And we can also determine the efficiency, which is the total power divided by the thermal input divided by the thermal input, which is provided by the heat source used to produce this temperature modulation. Now, I mean, we are all theorists, so we felt unable to run the experiment, but at least we could do a theoretical model of it. And if you do that, you get these jump trajectories here, these temperature traces. These are the results of the stochastic wave function simulation. And you get this characteristic plot of power versus efficiency. What you see is as the cycle time increases, the efficiency increases, and as it approaches 1, the power goes down to 0. That's because you get unit efficiency only in the limit where you do everything quasi-statically. The second observation that we get from this plot is that the power at fixed efficiency is uniformly suppressed as we increase the tunneling energy delta, which enters the Hamiltonian here. And the question for the next couple of minutes will be, can we explain this behavior in a quantitative manner using the data that we would generate from such temperature measurements? In the more general picture, we are now looking for a trade-off relation between power and efficiency, and that's in general a bound on power, which depends on the efficiency and some further parameters. Yeah, there must be at least one of such parameters to match the physical dimensions of these figures, but there can be more. And the obvious questions to ask in this context is, I mean, what is the shape of this function f? What are suitable choices for these parameters a? And importantly, how can we access them from experimental data? Udo has shown us yesterday that these questions can be answered in an elegant manner from the thermodynamic uncertainty relation and its generalizations, at least in a classical setting. And KG has just discussed another approach, and this shows that the answers to all of these questions are by no means unique. And now I would like to offer a third scheme, which I think has its appeal in its own and in particular covers the quantum regime. Okay, so let's move on. A bit of technicalities here. So what we do is we make the probably most simple model that you can make for this kind of system. So the state of the system obeys a quantum master equation. This is the unitary part, which is determined by the Hamiltonian of the system. Then you have this dissipative part, which is determined by these jump operators. Jump operators induce transitions between the two energy levels, and the scaling factors are chosen such that the dynamics obeys detailed balance. And for this kind of simple model, straightforward to write down the first and the second law. The first law just tells you that the extracted work is equal to the heat uptake Q. That's because the process is cyclic. And these quantities are defined as the time averages of the instantaneous heat uptake and the instantaneously generated power. In the second law, you have a total entropy production, which is just given here by the standard expression for the entropy production in the reservoir. The entropy production in the system does not play a role here again because the process is cyclic. Now, this quantity can be neatly divided into two contributions. One is the total work divided by the base temperature of the island, and the other one is what I will call the thermal input. This quantity is defined here as a weighted time integral of the heat uptake from the reservoir. And this weighting factor is somehow reminiscent of an instantaneous Carnot factor. Again, T is the base temperature, which is always smaller than the time-dependent temperature of the island, T of T. So what you see is, okay, this figure is obviously 0 if the temperature of the island is constant. And second, the second law gives you this upper bound on the corresponding efficiency. And this bound is attained if and only if the total entropy production is 0. So for these reasons, I believe this is a reasonable definition of the input of this engine. And I will now proceed with this. Okay, that was the ensemble level description, but because we have these quantum jump records, we have much more information. And we can now actually describe the system in terms of quantum jump trajectories, and this theory is here in a very condensed form in this little box. So an initial state psi naught evolves into a state psi t over the course of one cycle. This evolution is governed by some operator W of R, which depends on the measured records. And it includes two types of dynamics. Whenever we see a photon emission or absorption, the system instantaneously changes its state, and that's described by the jump operators. And in between the jumps, the system follows a continuous evolution, which is governed by this time-ordered exponential here, and this effective Hamiltonian. Obviously, this object is not unitary, so the norm of the state is not conserved under this evolution. And it turns out that the squared norm of the final state is in fact the probability density to observe a specific record for a given initial state psi naught. Okay, so once you have all this together, you can now evaluate the work output. This you do by just summing up the directed heat content of every exchanged photon between the system and the reservoir. That direction enters through this variable d, which is either plus or minus 1. And then you take the average of the sum over all possible jump records. That's what's indicated by the symbol E here. And that gives you the total heat uptake, which is equivalent to the work output by the first law. And you can play the same game for the effective thermal input, and you get the input of the engine. Okay, so far so good, but because you have the record, I mean, these jump records contain much more information than just these average variables. And for example, we could now look at distributions of individual quanta. So this is an important point. These distributions describe the size of the, or better to say, the amount of heat or thermal input that is transferred with an individual photon. These are not the distributions for the accumulated heat uptake or the accumulated thermal input that we would normally look at. But these are really single photon quantities. That's why I call them quantum jump distributions. And the meaning is simple. If I randomly pick one of these jump events in one record, then this distribution gives me the probability for that this jump event was accompanied by the exchange of heat Q. Okay, it's a bit unusual quantities, so that's why they have this peculiar shape. But I hope I can convince you that they can be useful tools. First of all, note that you can recover the average work and the average input if you just take the mean value of these distributions and multiply by the total activity, which is just the mean number of jumps per cycle. Okay, let's see what we can do with this. We can now derive bounds on entropy production, which go beyond the second law. The first one is this one here, which I call the coherence bound. And it shows that the total entropy production is bounded from below by the average of this thermodynamic flux sigma j, which is defined in this way. J plus is the instantaneous flux of emitted photons, J minus the instantaneous flux of absorbed photons. And so this object could justifiably be called the entropy production due to quantum jumps. And the remainder of the total entropy production, delta SC, which is now positive by virtue of this bound, can be identified as a result of decoherence. So this quantity comes from the decay of superpositions between the energy levels of the qubit, and it turns out it vanishes if and only if the state of the system commutes with the Hamiltonian throughout the cycle. Yeah, this is the quasi-classical limit where you have a classical two-level system and then this expression is totally trivial. This is just the usual entropy production in a two-level system then. But it is just a lower bound if you have coherence. Okay, next step, you can now show that this object delta Sj is bounded from below by the total activity times some function of one-dimensionless parameter, which I will call homogeneity. And this is just the square root of the ratio of the squared first and the second moment of the single jump distributions, these quantum jump distributions. This applies to any thermodynamic flux. For concreteness, you can always assume that X is just the heat exchange between the system and the reservoir. Now, what's the meaning of this parameter? It is one, obviously, only if this quantum jump distribution is delta shaped. And that would mean that all photons go in one direction. So you would see only emissions in the temperature trace, and every photon would carry the same amount of this quantity X. And the opposite limit, this is 0 if this temperature trace is fully stochastic and the average of this quantity vanishes. Okay, and these are all technical tools to this point, but what can we do with them? We can now use this bound and apply it, for example, to our thermal input. And then it's just a matter of rewriting to get this kind of trade-off relation between power and efficiency. Here you nicely see what parameters determine this trade-off. You have an object gamma, which is the total activity over the total time of one cycle. And that is a measure for the dissipation rate. You have the second moment of the thermal input, which gives you an energy scale. And you have this coherence parameter psi, which is the jump entropy divided by the total entropy. And it is 1 only in the quasi-classical limit where you have no coherence. And what you see here is that if you wanted to have efficiency 1 at finite power, yeah, because the tangent, the hyperbolic tangent vanishes at 0, you would have to have either a diverging energy scale, which can be accomplished essentially only if you have a protocol with infinite amplitude, or you would have to have an infinite dissipation rate. And in fact, this physical result is pretty much consistent with earlier studies. Okay, now you can push it to an extreme by looking for the optimal bound on power that can be derived from this inequality. And what you get is this expression, which is a bit more involved, and it involves also further quantities here. But I would like to emphasize that all of these quantities are well defined and can be determined if you have access to the jump records. Okay, now how does that play out? We now did the numerics, and the results are shown here in the last line. So you see for different values of delta, the black line is the actual power of the engine as a function of efficiency. The yellow line is this simple trade-off relation, and the red line is the optimal one, which is indeed pretty good and is in fact almost saturated in the regime of low efficiencies. And the next thing you see now, because when we turn up delta, yeah, I mean, then this two-level system will be in coherent superposition states during the cycle. That means that this factor psi is smaller than 1, and the larger delta is the smaller the psi will be, and that's why all of these bounds are uniformly suppressed in the tunneling energy delta. The quasi-classical limit where delta is 0, this is just the quasi-classical two-level system, and then you get the maximum power efficiency. So all of that's pretty consistent. Okay, so I want to use my last 2 or 3 minutes to dwell a bit on the general picture of this. So I have explained everything in this setting of the Qubit engine, but that was basically just to give you a concrete picture of what kind of setup we have in mind. In fact, the technical derivation is quite robust, and it goes through for arbitrary n-level systems. So all of these quantities are well defined. If you have arbitrary many levels in your system, you get this bound, you get these trade-off relations, exactly the same ones as before. And now what's nice is if you go to the linear response regime, so expand your Hamiltonian and you expand your temperature with delta W and delta U being small dimensionless parameters, you get back these bounds here where theta naught is now a quantity which is independent of the driving protocols, essentially depends only on equilibrium properties of your systems, whatever it may be. This bound was obtained here in an earlier paper by Udo and me. And finally, you can see that this efficiency-dependent factor has its maximum for lambda equal 1/2. And if you insert lambda equal 1/2, you get these efficiency-independent bounds on power. And again, you recover one earlier result. Okay. Finally, all of that also goes through if you have n reservoirs coupled to your system, provided that you're willing to add sufficiently many indices. So now the index nu is counting the reservoirs. And now you can reproduce with two reservoirs the standard thermodynamic setting of a heat engine, where you have a hot reservoir which provides some input heat QH, a cold reservoir that absorbs the waste heat QC, and in the middle you extract some work. And then these bounds can be expressed in terms of the conventional parameters. So eta thermal is now the standard thermodynamic efficiency, which is really work over heat uptake from the hot reservoir. Eta C is the Carnot factor. And you see, okay, if you reach Carnot efficiency, this object is obviously zero. And the slope at which you're approaching P equal to zero as eta goes to eta C is determined by the second quantum jump moment of the heat provided by the hot reservoir. Okay, now finally, I mean, you can reduce this bound if you notice that the hyperbolic tangent is bounded by x for x larger than 1, if you eliminate psi by setting it equal to 1, and then you get back these quite compact results, and this is exactly the bound that was obtained by Naoto, Keiji, and Tasaki earlier. Okay, so that's my last slide. So I want to close with this, as I think, quite nice unifying pictures. I just want to mention that you can derive many more of these trade-off relations from this bound here, depending on what fluxes you're considering. You can derive trade-off relations for refrigerators and all sort of thing. All of this is valid for arbitrary multi-level systems, for any number of reservoirs, any periodic protocols. And the assumptions that go in here is that you have weak coupling and detailed balance. Instantaneous detailed balance means that your transition rates satisfy this condition at every instant of the cycle. Okay, so much for that. Thank you very much.
Thank you very much.